Hey, hi everybody. I'm told I can start, so thanks for your time. I'm assuming you can see my slides okay. If you can't, please let me know. So I'm here to tell you a little bit about Unikraft and its status. Unikraft is a Xen Incubator project, and so the main focus of Unikraft is to try to make it so that you can build unikernels. These are specialized virtual machines as easily and transparently as possible, so you can run the workload you want to run on the hypervisor, Xen, for instance, and then to do so much more efficiently than you would with, let's say, a Linux-based virtual machine. So let's get started. Okay, so basically, if you want to reach high performance, one really good way to do it is through specialization, whether that's in software. You've probably heard of Mirage OS for OCaml. There's some JavaScript special virtual machines, or you want to do high performance network packet processing with DPDK, or in hardware, you have TPUs and things of that sort. Specialization is a really good way to get high performance. In the world of virtual machines, specialized virtual machines are called unikernels. And there are a number of goals that we reach with these, and one of them is that they should be easy to build and run. This hasn't always been the case, including some past project of ours. There should be almost no application porting if possible, and of course they should have great performance. So when we were building Unikraft, we have two major design principles. The first one was that we wanted a fully modular kernel so we could really specialize the entire software stack. And the second one is that we wanted to provide a bunch of high-performance specialized APIs to boost performance even further. So for the first one question is, why don't you just specialize Linux? And we did a dependency graph, and here it is, between the major components of Linux. And whenever there's a dependency between two of them, we put an edge, and a number above the edge is how many dependencies are between the two subcomponents. And basically what you can see from this graph is that it's really not so easy to take out a subcomponent to specialize it for a particular application. It takes a lot of engineering effort. Instead, Unikraft was built from scratch to be fully modular. This is just an equivalent graph with Unikraft. I don't really want to go into the details, but you can see the top graph is for Hello World, the bottom graph for nginx, and you can see it's much simpler and there's much fewer dependencies. Okay, so could have we built Unikraft from existing unikernels? And the problem was that they would require a lot of significant export to actually build. They were often no POSIX compliant, and the ones that were POSIX compliant, the kernels themselves, even though they were smaller than Linux, they were still monolithic. So it wasn't so easy to take bits apart. So we built Unikraft from scratch with, of course, some borrowing where we could. The second design principle was that we wanted to provide high-performance specialized APIs. So just to give you a little example, imagine your application is network bound. It would connect through glibc, POSIX sockets, the network stack, and eventually maybe a high-performance API. Of course, by the time it gets to the high-performance API, it's got so many intermediate layers that it's not going to go very fast. So if you had defined such a high-performance API and the application only cared about UDP, for instance, you could directly plug into it and go much faster. And this is what Unikraft really does. And here's its architecture diagram. You have the application at the top. We have support for two libcs, musl and newlib. And then under that, there's a POSIX compatibility layer so that we look to the application like we're Linux more or less. I'll speak about that later. And under that, you have all the major parts of Unikraft itself. And the black blocks are basically the different high-performance APIs. So for instance, if you cared about networking, as in the example, you could directly plug into UK NetDev to get high performance for networking. If you were interested, let's say, in accessing files very quickly, you could code against UK Block Dev and put a specialized file system, and I'll speak a little bit about that later. Or if you care about memory allocation performance, you could use one of several memory allocators that Unikraft provides. So going back to our goals, the first one was that it should be easy to build and run. And there's no easier way to show that than a very small demo. Basically, here we're using Craft, which is Unikraft's ecosystem tool, We're going to say I want to build an nginx unikernel here at staging. We're going to name it. And then Kraft is going to go ahead and download all the necessary sources and start building them right away. The moment it's done, it's going to actually just set it up and run it. There it is. And then just to make sure that it actually is properly running, we're going to curl the dummy website. And there it is. And then we're going to do it one more time just to make sure it's working. Okay, the second goal is that we don't want to have to, like in the past, port or spend a lot of cycles porting each application individually. So to this end, we have two approaches. The first one we call auto porting. What we do here is we assume that we have sources to the code like nginx or SQLite, and then we build with the native build system object files. We then code, and we actually build against musl. We then take those object files and we link them into the Unikraft build system. We also have a ported version of musl, so it works fine. And then under that, we, of course, need to provide syscalls because that's what musl expects. And so we have a syscall shim layer with syscalls, and under that comes Unikraft itself. The other side is binary compatibility, and this is for cases where the sources are closed, where we just have a binary. And here the idea is that we take an unmodified elf, and under that, we load it into Unikraft with an elf reader, and then we trap syscalls, and we trapped into the same syscall shim layer as before. So then the question really boils down to how much syscall support do we have and do we need? So this basically gray block that is common to both auto porting and binary compatibility. So to attack this, we did a bit of an analysis. So right now we support about 146 syscalls. This is a bit outdated. It's probably at around 170 now. And Linux has in the order of 350 syscalls. So there would seem to be a large disparity. But there was a paper a few years back that did an analysis, and it was saying that basically if you are around 150 syscalls, you can support around 50% of Debian packages. We did our own analysis, though, and to do that, we took the most popular popcorn Debian applications, and we plotted in here. You can see them on the x-axis. Is anything from databases and web servers and mail servers and so forth. And on the y-axis, we're plotting what level of percentage system call support we actually have currently in Unikraft. And you can see that it's basically mostly green. And the ones that are the bars that are not green, where we're still missing a few syscalls, just a few more syscalls would give us full support. So Unikraft is getting fairly mature in terms of providing a POSIX compatible interface. Of course, if all else fails, you could do a manual porting, which is what we did in the past. I'm not going to go into the details of it, but basically we did a survey of all the developers that manually ported things, and the takeaway message is that it's because Unikraft is much more mature, it's getting faster and faster and easier to actually manually port something to it. Just to give you a little taste of what we support right now, nginx, Redis, SQLite, applications such as those. We support programming languages and environments such as Python, and then frameworks such as TensorFlow Lite and PyTorch. And there's an increasing number of applications almost on a weekly basis. So the final goal, of course, is to retain great performance. And the question is, if we're doing this auto porting, are we sacrificing performance in the process? So to answer that question, we compared a manual port of SQLite that we did against the auto ported version. And to compare the two, we did a test where we do 60,000 insertions and we measure the time it takes to do that. As a baseline, we take Linux, which takes about a second. And then we compare it against the manually ported versions, both on NuLive and musl. It's also about a second. And then if we look at the musl autoport, this is the bar that matters, we see that it's also about a second. So in all, autoporting doesn't negatively affect performance. Okay, and now let's get into a little bit of evaluation and some numbers. First, looking at what happens when you don't necessarily specialize into the APIs. You just sort of port your application, automatically port it to Unikraft. What sort of benefits do you get transparently? So the first one is image sizes, and we compare against other projects such as other unikernels like Hermitax and Linux Lupine, if you heard of it. and also Linux, Mirage, and OSV. And we do it for applications such as nginx, Redis, and SQLite. And the takeaway message is that most Unikraft images take about a meg or two on disk, which is not very much. Unikraft boot times. Here, what we did is we compared a number of different hypervisors. I mean, we don't have Xen on here because we did this in the past, but I'm just going to quickly go over this. More or less with more modern stacks like Firecracker and QEMU MicroVM, we're booting in about 3 milliseconds. Minimum memory requirements. Again, Unikraft versus other projects in Linux. For various applications, we only need 2, 3, 4 megs to actually run standard off-the-shelf applications. You can compare that against the Linux Lupine unikernel coming in at 20 megs. Or you can compare against Linux Alpine, which is about 30 megs. So nginx throughput. So in this case, again, we're comparing against Linux in other projects. The average throughput in terms of thousands of requests per second. Let's pick just a few points. If we take a standard Linux on KVM, we get 100,000 requests per second. And on Linux native, without a VM at all, 175,000 requests per second. And Unikraft is close to 290,000. Redis performance, just real quick, the main takeaway here is that we are running just a little bit faster than Linux native, which is quite good. Okay, what about boot times? We wanted to see if using the different allocators that Unikraft provides matters. You can see that the default one, which is the binary body allocator that we took from MinUS from Xen, is not necessarily the fastest to boot. It's still 3 milliseconds. So one thing we did is we coded a specialized but very simple boot allocator, a memory allocator, which is very quick. And then we wanted also to test application performance with different allocators. And you can see here, in this case, memalloc is the best allocator. And it doesn't matter which allocator you use. And with Unikraft, you can, at compile time, choose different allocators and then test which one does the best for your application. And finally, just real quick, I wanted to talk a little bit about what happens when you do code against the specialized API, what sort of performance gains you can get. In this case, we're in this domain. We want to retrieve static files as quickly as possible. So we coded a specialized file system called SHFS, which is based on a hash table. And here we're going to compare Unikraft against Linux, and we're going to measure in cycles how long it takes to retrieve a file, whether it's there or not. And on Linux, using the VFS, we're in the range of 2,600 cycles for when the file is there, and when the file is not there, it's about 4,000 cycles. We also did a measurement with no mitigations because those cause a big performance hit. On the Unikraft side, if we use our own VFS system, we do get about half reduction with respect to Linux. But the real big gains come when we use the specialized file system directly on our BlockNet API, and there you get almost an order of magnitude reduction. So specialization obviously really matters. So that's enough for performance. We then decided to do a test on the cloud. Basically, we are in the process of upstreaming Xen networking support this week and the week after this, and these are the results from that. So we went to AWS, to the marketplace, and we created a Unikraft Xen nginx image. So you can see it there on the dashboard. And what we did was the following. We took two large instances. On one, we put a standard AWS marketplace nginx on Debian image. And on the other one, we put Unikraft. And we basically got twice the throughput. On another test, we took the same large instance, but this time we compared against the medium one. On the large one, we put, again, the Debian image. On the medium one, Unikraft, and we roughly got the same performance. And then the question was, does this performance actually translate into a lower infrastructure bill? And the answer is yes. We looked at our bill when running these tests, and we ended up paying about $87 for the Linux Debian test and only about $43 for Unikraft, which is about 50% less. Okay, so just in terms of platform support, I mentioned we support Xen, and this is where we did all these tests I mentioned just now. We do have under Unikraft KVM support, so you can run things on GCP and on DigitalOcean. And we're starting to put a little bit of effort into supporting Hyper-V. In terms of the ecosystem, I mentioned earlier that we have a craft tool that wraps around Unikraft so that it's easy to build, download, and run Unikraft unikernels. So in fact, if you wanted to try Unikraft, you would go to github.com/Unikraft and you would clone the craft repo. And you can say things like craft list, and it'll show you all the different platforms that are supported, libraries, and applications. And then you can sort of pick and choose what you want, as I showed earlier with the demo, and it'll go ahead and build everything for you. Also, craft is something that we use to release tarballs and packages that you can just download directly, so you don't need to actually compile anything. And there's a lot more commands on there, so you can go in there and check it out. So the other part that on Unikraft we wanted to do, beyond supporting different applications easily, is integrating with existing orchestration frameworks that people might be using. So on the build part, I showed that there's Craft, and that's relatively easy to use. But we wanted to make sure that if people were using Kubernetes, that it was easy to deploy that as well. And for monitoring, lots of people use Prometheus, so we're integrating into Prometheus. So I already showed Craft for building, so let's move on to Kubernetes. Here's just a short video. We have a node called Node 1 already running. We have a number of pods, which are essentially virtual machines running on there, 11 at this point. And what we're going to do is we're going to go to the console and use the standard kubectl command. First, we can list pods that are there, the virtual machines. There's 11 of them. And what we're going to say is we're going to create a Unikraft pod, or virtual machine, essentially. And now we have 11 of them. One more. There it is. Unikraft is up and running. And then if we go back to the dashboard here, you can now see that there's 12 total. And what's nice about this is that basically we're not running a container at all. We extended Kubernetes underneath to natively run a virtual machine. In terms of monitoring, we are starting to do some early stage Prometheus integration, so we can now output some stats to Prometheus. And I think I'll leave it at that for now. There's an early screenshot there. And then just to finish real quick, the open source project, just to give you a little bit of a project history, in 2017, we built this as a launched internal project at NEC. We quickly started talking to the Xen project and the Linux Foundation between 2019 2019, and we became public. And in 2020, we spent a lot of time maturing all this syscall support and support for applications and so forth. And here we are in 2021, where we're trying to do all this integration with orchestration frameworks. Okay, this is just a little graph showing the growth in terms of stars, where we've seen some decent growth in the past months. And recently we built a paper that was accepted at this top level systems conferences recently, and we were happy that we also received the Best Paper Award. So if you want to know a lot more details about Unikraft, you can go check it out. We also made sure that the results in the paper were reproducible. So there's a separate repo that you can go and download, and you can just sort of run a script, and it'll not only build the images, but actually run the test for you and get the performance results that we say we got. Okay, so with Unikraft, we think high-performance POSIX unikernels are now a reality. If you want to know more about the project, just go to unikraft.org. Of course, all the code is open source, so go to github.com/Unikraft to download it and try it out. And the artifacts of the paper are actually at this repo too. So thank you very much, and I'd be happy to take any questions. And if there are no questions, Naomi, let me know what I should do.
Hello. I have a question. I'm not sure if you can hear me.
Yes, I can.
My name is Mahir. I work for Amazon. So previously, I played around with OCaml and MirageOS a bit, and RAM kernels too. And OCaml was painful, to say the least. So when you started the project in 2017, was there anything, any goal that you have set that weren't available or present on those projects? Because back then, I think both MirageOS and RAM kernels were available.
Yeah. So rump, we kind of at the time thought you can pick one of two. I mean, you can pick security, or you can pick compatibility, or you can pick performance, but you cannot pick two or three of those. With ramp, you have good compatibility. It was essentially a BSD kernel, right? And right. So you easily build things onto it. But actually, when you did performance tests, it was really not that good at all, right? Then you went to OCaml and you got nice type safety sort of features. But you didn't have good compatibility with standard applications because everything needed to be in OCaml, and the performance wasn't all that great because it wasn't their goal anyways. And then you had unikernels that we were putting together from our group and others that performed really well. They were targeted at one application, say a web cache, but whenever you wanted to go to another application, you needed 3 months engineering work to get that other application working. So there wasn't any single project that was kind of making it sort of easy, relatively easy to use, low port time, and you would still keep the performance. And that was the purpose of creating Unikraft.
Got it. Thank you. Yeah. It sounds like a good middle ground in between.